the Arctic and why it should matter to all of us that it's changing so fast. So this is a topic that I've been studying really just for the last decade or so, as Tracy mentioned, looking at the Arctic and the fact that it's warming so fast, the ice is disappearing, all three types of permanent ice there are just disappearing before our very eyes, which I will show you some of, and looking at why the rapid changes in the Arctic matter so much. And this picture gives away one of those connections to all of us, especially for those of us who live near the coast. Sea levels are rising, that's accelerating, and that's partly because of the rapid warming that's happening up in the Arctic. But what I have been mostly interested in studying is how the Arctic's warming is affecting extreme weather events and sort of general weather conditions around the mid-latitudes of the Northern Hemisphere. So just to sort of set the stage, this was the just unbelievable heat wave that struck the Pacific Northwest this summer, this past June. This map here is showing you temperature differences from normal. And so you've got the North America here. This red blob is where the temperatures were so much higher than normal in the Pacific Northwest. But what I also want you to notice is that not only was there a very unusual temperature situation in that area, right next door, it was actually colder than normal. So one thing I want you to remember from today is that when we have an extreme event of one flavor, you can almost bet on the fact that we're going to see unusual weather patterns of the opposite type, usually right next door. And in this one, you can also see that it was very warm in New England at the same time. So why did this happen? Why did this unprecedented heat wave hit the Pacific Northwest? Well, when you think about weather in the Northern Hemisphere, except for hurricanes, your mind should go straight to the jet stream, because the jet stream really is what creates all of the weather that we experience in the mid-latitudes especially. And this map here done by CBS News shows you in words where the jet stream was during this severe heat wave. And what you can see is there was this very convoluted pattern in the jet stream where it took a large swing northward, almost up into Alaska. And one thing we know about the jet stream is that it's generally the boundary between the air to the south, which is very warm, from the boundary to separating it from the very cold air that's much farther north. And so when the jet is north of you, as it was over the Northwest in this case, it allowed all that warm air from the south to penetrate much farther northward than normal and create this very unusual situation. But you remember that cold area that I showed you that was right next door? Well, that's because the jet stream dipped down just to the east of that big northward bulge, and it brought all that cold air from the Arctic with it. And that's what created that cold air that was settled down over New Mexico and Texas. So moving on to another extreme event that happened this summer, you'll probably remember that Germany and Belgium and Holland were struck by some very severe flooding. It was a very unusual situation. And again, we have to think about what was the jet stream doing at this time. And once again, it was in a very convoluted pattern. You can see Spain right here in the background. There's the UK. And this jet stream was dipping way up over Europe at this time, but there was also this cutoff eddy in the flow, which sometimes happens when the jet stream takes one of these big northward swings. And in this case, the low in the upper levels was bringing moisture in from the Mediterranean. This low was sitting there for days on end and brought a lot of moisture up into Germany and Belgium and Holland, where they had that extreme flooding, where it just rained for days and days. So again, it was another very unusual jet stream pattern. And getting a little closer to Minnesota now, and something that you can relate to, in February of this past year, you'll remember the very severe cold spell that struck the middle of the country. We're now looking at temperatures here in Fahrenheit, and you can see very clearly that the middle of North America was basically covered by this much colder than normal air. It got down to -2 degrees Fahrenheit in Dallas, Texas. You know, this is not unusual for you all up in Minnesota, but for Dallas, Texas, it was absolutely devastating, and it froze pipes. It took down the power grid. It was a very, very unusual cold snap. In fact, it was colder in Dallas at this time than it was in parts of Greenland and parts of Alaska. So that just tells you how unusual this was. The other thing that made it unusual was that it extended all the way down to the border with Mexico, and it lasted a really long time. So what was going on with this particular extreme event? Well, yes, the jet stream again was in a very wavy pattern. Now we're seeing it, the jet stream represented by the storm track here. And you can see that it's dipping way far south, which allowed that Arctic air to plunge much farther south than it normally would. But we also have this other thing happening here, shown in pink, the polar vortex. And this has become a common term around the dinner table just in the last several years. And I have to say that it's not always used correctly. So one thing I want to do today is make sure everybody here knows what the polar vortex really is, because it played a very important role in both the persistence and the severity of this particular cold snap that happened in February. So what is the polar vortex anyway? So here we are looking at a schematic, looking down on the Atlantic Ocean. This light blue ring around the North Pole here is supposed to represent the jet stream. It's never circular completely like this, but we'll go with it. The jet stream is here all year round. It's always with us. And it sits about 5 to 9 miles above the surface, so up where the jets fly. It's a river of very strong winds. But sitting on top of that, up much higher in the atmosphere, between 10 and 30 miles above the surface, we have another ring of very strong winds that encapsulates or surrounds a pool of very cold air that is only there in the winter. So the stratospheric polar vortex is the complete name for this, only exists in the winter, whereas the polar jet stream is there all year round. Now, most of the time, the polar vortex sits up there and really doesn't bother anybody. It doesn't affect our weather, but every once in a while, it will become disrupted. And by disrupted, I mean it can either stretch and take on kind of a bean shape, or it can even split into separate circulations that have this very cold air trapped inside of them. And when that happens, those pools of cold air tend to drift southward and take that very cold air with them. And that's exactly what happened this past February. We had one of these circulations from the stratospheric polar vortex drift down over North America, and it made that dip in the jet stream even stronger, brought all of that extra cold air and made that cold wave even more cold. And over in Siberia, another piece of the vortex drifted down over there and caused cold temperatures as well. And you'll notice, again, like I showed you in some of those examples, not only do we have these cold southward dipping parts of the jet stream, but right next door, we see these places where the jet stream dips or extends farther north, and that allows the warm air to move much farther north than it normally would. So if we look at the big picture now of the temperature differences from normal that were happening at this time, you can see over North America, it was much colder than normal, same over Northern Eurasia. But again, we have these extreme events of the opposite flavor happening right next door, where those northward swings in the jet stream were bringing a lot of warm air much farther north. And we see another very warm situation over China. So keep that in mind. Extreme events are never in isolation. And it's not your imagination. We really do know that extreme weather events are happening more often. And it's not just scientists who care about that. Companies such as insurance companies are keeping close eye on this situation as well. And that's where this graph comes from. So going back to 1980, they've been keeping track of extreme events of various sorts. And these red bars here are showing you any changes that might be happening in extreme events that are not related to weather. So these would be things like volcanic eruptions or tsunamis or earthquakes, things like that. And these other bars are all related to weather in some way. And what we see is that just since 1980, we've seen a tripling of the frequency of extreme events related to weather. So we really are seeing an increase in extreme events. So now I just want to set the stage a little bit and go back in time quite a ways, 20,000 years, a little more than that, and look at how the Earth's temperature has changed over this time period. So on the far left here is 20,000 years ago. The Earth was a little over 3 degrees colder than it is today. That was the last time we had an ice age. And all of Minnesota was covered by a very thick layer of ice back then. And it extended very far south, right down to where I am right now in southern Massachusetts. And then gradually the Earth warmed up until we got to what we call the last interglacial period, which is a relative warm period in the Earth's cycle. And since then, the Earth has been getting cooler over time. So this is really important. The Earth right now, if only natural causes were in play, and the natural causes were what caused these changes in Earth temperature up until present day, if only natural causes were happening right now, we would be in a cooling cycle on Earth. But we all know that that's not what's happening now. We've seen this incredibly abrupt shift in the Earth's temperatures. We've warmed up much faster than any other time period that we can see going back in this record for sure, and farther if we look at even longer time periods. And if we stay on this trajectory, we're looking at temperatures around 3 degrees warmer than pre-industrial time if we keep emitting greenhouse gases at the pace we are doing that. So these natural causes that created this change in the Earth's temperature over this time period are things like changes in the tilt of the Earth's axis relative to its orbit around the sun, or changes in the Earth's orbit shape, for example. Sometimes it's more round or circular, sometimes it's more elliptical. And all of those things can change the way the sun's energy is distributed around the Earth and lead to these temperature changes. The other thing I want you to notice is that it doesn't take much of a temperature change to make the Earth's climate very, very different. So the last ice age, as I said, was only a little bit more than 3 degrees colder than it is now. So here we are already over 1 degree warmer than we really should be, and we're heading towards 3 degrees warmer than pre-industrial times. So this is going to cause some very major changes in the climate system. And I know there's quite a variety of people listening in today, so I just wanted to make sure everybody has a decent understanding of what greenhouse gases are and why they're such a big deal, why we care so much about not putting any more of them in the atmosphere if we can help it. So here's just a schematic of how the Earth's energy system works. We know we've got the sun sitting up there providing all of the energy that warms the Earth. The sun is about 10,000 degrees Fahrenheit roughly. And we know that hot objects like the sun, the energy they emit, light that we see with our eyes, is very short wavelengths. So hot items emit energy with very short wavelengths. And this energy penetrates right through our atmosphere and gets all the way to the surface. Some of it is reflected by clouds, but most of it makes it to the surface. And that's what warms the Earth. Now, the Earth, on the other hand, is much, much cooler than the sun, and objects in the range of temperatures that the Earth is also emit energy, but cooler things emit energy with much longer wavelengths. And it just so happens that the infrared energy, as it's called, with these longer wavelengths, is absorbed by greenhouse gases, these greenhouse gases in the atmosphere. So those include water vapor is the most important one. Carbon dioxide, methane, and several others. So as this energy from the Earth tries to leave and go to outer space, it gets absorbed by these greenhouse gases in the atmosphere, and they act like a blanket on the Earth. And just like a blanket on your bed, if you add a thicker blanket, you're going to be warmer. Well, as we add greenhouse gases to the atmosphere, it is warming the Earth. And that is why the Earth is warming right now, because we have been increasing those greenhouse gases quite a bit from what they were only a century or so ago. So I did mention that water vapor is the most important greenhouse gas. This is the invisible phase of water. So we're not talking about clouds here or rain, we're just talking about the gas itself. And this animation is showing you where water vapor is most abundant around the Earth. And these red and yellow colors are showing you that the water vapor is very abundant around the tropics. If you've ever been to the tropics, you know it's very muggy and sticky there. Well, that's because there's lots of water vapor in the atmosphere, and of course it's warm. And this animation I chose, it's actually from last year's September, so September 2020. I chose it because it has some interesting things going on. Here's North America. That little black dot is Bermuda right there, and it's about to be affected by Hurricane Teddy, which is that swirl right there. Hurricane Sally had just moved into Louisiana, and there's some other tropical disturbances out in the Western Pacific. You can also see these interesting tendrils of moisture that extend all the way from the tropics almost up to the Arctic in some cases, and also down into the southern high latitudes. And they are caused by storms. So one of the jobs of storms is to take that extra water vapor that's building up in the tropics and transport it away up into the areas that don't have as much water vapor. So all of these swirls and tendrils are all caused by the storms that come through the temperate areas of the Earth. So the reason I'm going on and on about water vapor is because it's actually a very, very important part of the story of climate change. And in my opinion, it is a very underappreciated part of that story, because the water vapor in the atmosphere is increasing quite dramatically. Since about the mid-1990s, we've seen about a 4% increase in water vapor averaged around the globe. And this is a really important thing because, as I said, that water vapor is also a greenhouse gas. So it's adding to that blanket around the Earth and making global warming even more than it would be otherwise. That water vapor is also the main fuel that storms use to generate winds and to become strong. And so when we have more water vapor in the atmosphere, it means that storms just have more energy to work with. And so we expect to see stronger storms as a result of this. And that water vapor is also providing the moisture for precipitation. And as a result, we have a very clear signal of climate change appearing in the frequency of heavy precipitation events. So across the United States, especially in New England and across the upper Midwest, we can see that there's a very large increase in the frequency of these heavy precipitation events going back to the late 1950s. And if we look at snow even, this happens to be for the Northeast, but I think the story probably applies to Minnesota as well. Each of these colored dots represents one of the main big cities in the Northeast. And there, for each city is plotted here the 10 biggest snowstorms that have occurred in each of those cities. So going back to the late 1800s, we see that these dots tend to cluster in the last couple of decades. So that is suggesting that we are actually seeing a tendency for the heaviest snowstorms to also occur in more recent times. And this is most likely related to the fact that we have more water vapor in the atmosphere. So if you're interested in the water vapor story, I now have a third article that just came out in Scientific American just last week. I was very excited to see that they featured it on the cover of the magazine, and it's all about the various ways that this increasing water vapor is playing a big role in climate change. So just thought I'd bring that to your attention. If anybody wants to get a PDF of it, I can make that happen. All right, so I want to get back to temperature now. And this is obviously a global plot of temperature change, but it's a little different probably from others that you've seen. So this one is showing you how temperatures have changed in a particular place relative to the globe as a whole. So what that means is that these blue areas are warming slower than the globe as a whole, whereas the redder areas are warming faster than the globe as a whole. So what you notice right away is that the land areas are warming much faster than the ocean areas. And what's particularly standing out here are these bright red colors up along the Arctic, showing us that the Arctic is warming much, much faster than just about anywhere else on the planet. And we can look also at the Arctic all by itself during the summer. This is showing how the temperature of the Arctic has changed since the late 1940s. In the summer of 2020, which was just 2 summers ago now, we smashed the all-time record. So the Arctic is heading off into uncharted territory. And this is really kind of a literal explanation of what's going on. And associated with that, of course, is, as I mentioned, the ice in the Arctic is melting. This particular animation here is showing you how the thickness of the sea ice, this is the ice that floats on the Arctic Ocean, has been changing since the late 1970s. So in this plot here, you can see there's Greenland, there's Scandinavia on this side, and Alaska would be over here. These colors are representing the thickness of the ice, where the yellows and whites are the thickest ice types, and the blues and purples are where the ice is thin. And what you notice right away is that as we go through time here, those thick ice types are basically disappearing. The ice is so much thinner now in the Arctic, something like 60% thinner than it used to be only about 40 years ago. It's just a huge change. And not only is the thickness changing, but the extent of the ice is also changing dramatically. So in the upper right corner here is looking again down on the Arctic Ocean. There's Greenland and Alaska. And this is what the ice cover used to look like back in the 70s and early 80s during the summertime. In September is when the ice melts back to its smallest extent. So here's what it used to look like at that minimum extent. But as we jump forward here now to 2012, which was the year that we've observed the least amount of ice coverage ever recorded in the Arctic Ocean, we can see that there's just this huge area of red and yellow colors here, indicating where there used to be ice and now it is no longer there. The difference between the ice coverage during these 2 time periods is roughly about half. So we've lost half of that ice cover in only about 40 years. And then if we multiply this by the thickness that I just showed you, we get that the ice volume has declined by almost 3/4 in this very short amount of time. This is a huge change to a very important part of the climate system. And by losing this very white surface, it means that in the sun that used to come down and hit this ice and get reflected right back to outer space is now instead going into the ocean and being absorbed, warming that water and melting even more ice, setting up a vicious cycle that leads to more and more ice melt and more warming. And this is one of the main reasons why the Arctic is warming so much faster than anywhere else on the planet. And not only is it warming the Arctic Ocean, but the darkening of the Arctic means that the globe as a whole is absorbing much more of the sun's energy than it would if that ice and snow cover on the high latitude land areas weren't there. That's resulting in global warming being somewhere between 25 and 40% stronger than it would be otherwise. It's also causing the Greenland ice sheet and the glaciers around the Northern Hemisphere to melt faster. That water, that ice, when it melts, goes right into the ocean and directly contributes to sea level rise. And we're seeing sea level rise globally also accelerate. We're also seeing that extra warming in the Arctic thawing the frozen soils of the high latitudes. This is called permafrost. And this is a very important story as well, because that permafrost soil contains a lot of organic matter. So this would be dead plants and dead bugs. And most of the time, while it's frozen, it's just sitting there year after year. But now that the permafrost is thawing, the microbes in the soil are starting to digest that organic matter. And the result of that is a release of even more carbon dioxide and methane into the atmosphere, both of which, of course, are greenhouse gases. So this sets up yet another one of these vicious cycles or positive feedback loops that involves the thawing of this permafrost. So this is a very concerning trend that we're observing, because we really don't have a good handle on how fast this thawing is going to happen and just how much carbon is trapped in those soils. And then we get to the part that I've been thinking about a lot lately, and how that rapidly warming Arctic may be affecting the jet stream winds, which, as I showed you in the very beginning, are very important to causing some of this extreme events that we've seen this year particularly, but over the last several years. And I want to try to explain the idea behind why we think the rapidly warming Arctic may be having this impact on the jet stream. So if we can imagine a layer of air that extends from, say, Minnesota all the way up to the Arctic, we know that it's generally warmer in Minnesota than it is in the Arctic, and we know that warm air takes up more space than cold air does. So if you were sitting on top of this layer and looking towards the north, you would be looking down a hill. Well, the air sitting on top of that layer wants to flow down that hill, and that creates a wind. And because the Earth is spinning, that wind turns to the right in the northern hemisphere. And this is what creates, this is the main reason why we have a jet stream, because of this difference in temperature between the Arctic and the warmer places farther south. But now we need to think back to what's happening in the Arctic. The Arctic is warming much, much faster. So this layer is getting thicker, faster there than it is in Minnesota. So that has the effect of making that hill in the atmosphere less steep. So there's less force driving that wind. And as a result, we expect to see the west winds of the jet stream weaken. And in fact, this is something that we have been able to measure. And we know that when the jet is in one of its weak phases, it tends to take these bigger north-south swings as it travels around the northern hemisphere. It's more easily deflected by things like mountain ranges or even temperature differences out in the ocean. And so we tend to see these bigger waves in the jet stream like this when the jet is weak. And as you'll remember back to the very beginning of when I started talking, these big waves are often associated with various types of extreme weather events. But why do we care about these waves? And I've been talking a lot about these waves in the jet stream. Well, you know that they're associated with extreme events, but more generally, they have a lot to do with the weather that we experience on a day-to-day basis. So we've already talked about how the jet stream, which is this purple arrow here in the schematic, separates the warm air to the south from the cold air in the north. So when the jet stream is south of you, like in this diagram here, Minnesota would be probably a lot colder than it would normally be. But also the waves themselves create the high and low pressure areas that we would see on a TV weather map. So in this part of the wave where the winds are coming from the northwest, we tend to see high pressure associated with clear blue skies and dry conditions, whereas in this part of the wave where the wind is from the southwest, it tends to bring in a lot of tropical moisture, and it creates dynamics in the atmosphere that cause low pressure at the surface. So this would be where you'd find your stormy conditions. So where these parts of the wave are located relative to you makes all the difference in the world as to what kind of weather you're experiencing. So not only does the shape of the wave matter, but also the size of the waves. When we get these very large waves in the jet stream like this is showing, they tend to shift very slowly from west to east. And what that means for us down on the surface is that the weather conditions that we experience then are going to last a long time. They're going to last longer. We're going to have very persistent conditions. So in this example, where we'd expect to see dry and settled conditions out in the western states, this is exactly what's been in place most of the time over the last couple of years. And that's led to the long-term drought that the western states have been dealing with. But sadly, the real jet stream is nowhere near as simple as that nice schematic. The real winds of the jet stream, which are being shown here in this animation that NASA put together, those red and yellow colors are where the winds are the strongest, and you can see very clearly where the jet stream is, but you can also see that it's a very unruly, messy, chaotic situation. So you could think about maybe how we might go about measuring whether there are some changes happening in the jet stream or not. It's not straightforward, it's not easy. And so that's why the answer to this question that we've been working on, and that is how the Arctic might be affecting the jet stream, has not yet been answered, just because it is such a difficult beast of a thing to try to get your arms around. So I know this animation is really quite hypnotic. There's so many cool things to focus on, but what I want to show you, in addition to the messiness, is there are times when the waves are small like this and they move quite quickly across the continent, and that there are other times when the waves get really big and they tend to stay put over one place for quite a while. And that's the idea that I was just talking about, how the bigger waves tend to move much more slowly across the continent and thus create more persistent weather conditions. So just another little schematic to kind of drive this point home. This was a case back in November 2013 when there was a lot of cold air bottled up over the Arctic. We're looking down on the North Pole again. Here's North America. And these red arrows here are showing you a relatively straight jet stream, basically encircling that cold air. But in this other case on the right here, which was another very severe cold spell that struck the Midwest, you might even remember it. It was the case when the polar vortex really became part of our dinner table conversations. Again, the Arctic was relatively warm in this case. The pools of cold air shown in blue here had migrated far southward, and the waves in the jet stream were much larger. And so this situation persisted for a very long time and led to that very long-lived and extreme cold spell that happened that year. And if we compare that to this past cold spell that happened in February, we can see these red and yellow colors again are showing us the locations of the jet stream. There's North America, just like on this one. And you can see that the pattern was incredibly similar, actually, to the case of that extreme cold event back in 2014. Okay, so did I just miss one? Nope, okay. So I want to kind of shift gears a little bit here, getting down to the end, and kind of take a look at the future and what does our future hold. And I want to go back to sea ice to help us think about what we are expecting to happen in the future. And so what this is showing you here is how the extent of sea ice, or the area covered by sea ice, has changed going back to the 1900s, basically, all the way to present day, which is about here, and then going on into the future. This black line here is the actual area of ice. It's the real world. It's what's actually happened. And we can see again this dramatic decline in the area of the covered by sea ice in the Arctic. And this cloud that surrounds that black line are simulations by these very sophisticated computer programs that we use to try to simulate the Earth's climate system and understand why it works and how different events may be changing in the future. So you can see that the climate models actually did a pretty good job simulating how the sea ice had changed in the past. So now, as we look forward in the future, though, we see that we have different colored lines that represent different possible scenarios for the future. And each of these scenarios really depends on just one thing, and that is what we do, what humans do, and how, whether we'll be able to curtail our emissions of greenhouse gases or not. So let's start out by looking at this red line. This red line is what I call the do nothing line. It's what will happen, probably something like this, if we keep emitting greenhouse gases at the pace we're emitting them today. We expect to see a summer with a summer in the Arctic when there is virtually no sea ice left, probably by somewhere between 2040 and 2050. this is almost certainly going to happen, and there's not too much we can do about that at this point. But then there's this other green line here. This green line is what's possible. This is what we could achieve if we were all able to basically pull out all the stops and really dramatically reduce our emissions of greenhouse gases, stop cutting down trees, stop deforestation. This is probably the best that we can hope to achieve. And you see that for the next couple of decades, all of these lines are basically doing the same thing, which means that we cannot change what's going to happen in the near future, most likely. We are going to see more sea ice lost, we're going to see more sea level rise, we're going to see more extreme weather, but there will come a time where the actions that we take today will have a big impact on what the years look like going out to the end of this century. So I think, you know, what this is trying to say is that we do have an opportunity to maintain some stability in the climate system, but right now we're on this red track and we need to pull out all the stops, as I said, to shift over. There are some signs that we might be making a little bit of progress. This is the annual emissions of carbon dioxide from fossil fuels starting in 1960 up to nearly present day. So we've got gas, which is called natural gas. I don't call it natural gas anymore. I call it fossil gas because natural gas just sounds like it's fine. It's okay to use. It is not fine. We need to get off of fossil gas as we do oil and as we do coal. But there has been a slight decrease in our emissions of carbon dioxide just in the last year, which is good news, but it's nowhere near enough. And to explain that, and this whole concept of net zero that you've been hearing a lot of because of the upcoming climate talks in Glasgow, Scotland, you can think of, we'll use a bathtub as an analogy for this net zero concept. So if you've got a bathtub filled with water, you can think of that water as the amount of carbon dioxide that's in the atmosphere right now. That bathtub has a drain. The drain lets out a certain amount of water because the drain is not going to change how big it is. This big arrow up here is representing the emissions of carbon dioxide that we are putting into the atmosphere right now. You can see the arrow going in at present is much larger than the arrow going out. So the amount of water or carbon dioxide in the bathtub is getting deeper. So what we need to do is make this big arrow that's dumping water or carbon dioxide into the bathtub the same size as the drain in order to achieve net zero. So you can see that right now that arrow is much, much bigger than the drain arrow. So we have a long way to go. This little dip here is nowhere near enough to make that big arrow small enough to achieve net zero. So that is what net zero is all about. And if we do stay on that red line rather than the green one, this is what we can expect to see happen for Minneapolis. The summers in Minneapolis are expected to warm up, obviously, and it'll be by the end of the century, by 2100, which is only 80 years from now, your summers will be much more similar to those in Mesquite, Texas, which doesn't sound great. So we need to make sure we don't follow that red arrow, that red line rather, for the future, that red scenario. So what can we do? I'm sure a lot of you have already given this a lot of thought, but we have a lot of personal choices that we can make in terms of our transportation. How much we fly in airplanes is probably one of the biggest things that we can change to make a big difference. It's been estimated that one transatlantic flight by one person in a normal commercial aircraft emits enough carbon dioxide to melt about a dinner table sized area of sea ice in the Arctic. So it makes a big deal. Traveling by air is a very, it sends a lot of carbon dioxide in the atmosphere. But you know, choosing our cars, what type of car we drive, how much we drive, whether we can make our homes more efficient, our appliances more efficient. I mean, it all comes down to using less energy, because that energy that we use, actually, if we can not use it or not use as much, saves even more energy, because it takes a lot of energy to make the energy by the time it gets to your plug in your wall or the gas tank in your car. At the community government level, there's also a lot we can do. And this comes in both terms of adaptation, so looking around our communities for vulnerable infrastructure, planning proactively to improve the resiliency of some of that infrastructure, because we know that extreme weather is going to continue to become more extreme, at least for a couple of decades. And so anything we can do proactively is going to make the damage from that extreme weather less damaging. We need to transition over to municipal energy resources that are more resilient, more renewable rather than fossil fuel based. Again, more conservation by our municipal energy use. And we can all get involved a lot more than we are. So joining committees in your town, or maybe even run for office, say your planning board or your select board. It's amazing how much difference one person can make, especially in a small community. And then of course, moving up to the bigger government levels, we all need to get out there and vote for leaders who understand the climate crisis is a crisis and who are going to make some difficult decisions to get us onto that green line. One thing we can do really quickly that would make a big difference would be to stop subsidizing any activities or infrastructure that supports the fossil fuel industry, and instead use those subsidies to incentivize renewable resources. We're still spending billions of tax dollars on subsidies for fossil fuel companies who are making plenty of money. They don't need those subsidies anymore. We need to price carbon appropriately, and there are a lot of ways being proposed to do this that don't hurt individuals. So pricing the carbon at its source, and then using that revenue that's generated to return to people so that they're reimbursed for, say, higher fuel prices. And then this, I don't think I have to tell this group, because you are here, you are educating yourself, and you need to take the information that you have either through your own work or in listening to seminars like this, and then go talk to people, go talk to your family, go talk to your neighbors, make sure they are getting information that's based in fact and not based on something else. And there's certainly plenty of that out there. So this is my very last slide. This is a painting that was sent to me by one of the son of one of my graduate students a couple of years ago. And it made me very sad, because it was his vision for his future. And so I want to ask all of you to do everything you can do to keep us on that green line and stay away from that red line, so that this guy and his generation will be getting something that's a little brighter future than what this picture indicates. So with that, I am going to stop sharing, and I look forward to hearing some questions from you all.
Right, thanks very much, Dr. Francis. If anyone had, we have a few minutes for questions. If people could use the reaction button maybe to raise their hand, and I'll call on you in the order that you pop up onto my screen. So I see Stefan Lees first. Go ahead, Stefan.
Hey, thanks for the talk. So about halfway through your talk, I saw this slide where you mentioned the warming, especially over the north. And then there was this one cold blob southeast of Greenland.
Mm-hmm.
So I'm wondering, I assume that's the reduced ocean transport that doesn't transport that much warm water up north. So I'm wondering if you have any thoughts on.
Yes, that is another really interesting recent feature that's kind of appeared in the North Atlantic. And there's a lot of research going on right now about what's causing it and what's going to happen in response to it. It looks like the leading contenders for the cause are an increased amount of fresh water coming from melting the Greenland ice sheet and also from extra river output flowing into the Arctic Ocean, which then eventually flows out into the North Atlantic. And so that extra fresh water that ends up in the North Atlantic there is lighter than the saltier water beneath it. And so it's actually inhibiting the mixing, the vertical mixing of the warmer, saltier water from down below up to the surface. So it's acting kind of like a cap on the ocean in that area. And so it's very interesting because whenever you change the temperature anomalies or distribution in the ocean, you are also going to change the response of the jet stream to it, especially something that is as conspicuous as that. It's really a strong cooling area. And so if you think back to that atmospheric hill that I described, you can imagine that over that blob of cool water there, the air above it is going to be cooled, and so it will be reduced in terms of the thickness of that layer. So south of it, actually, it will help to enhance the winds of the jet stream. And that's why we've had a couple of papers recently suggest that that cold blob, it's called, may actually cause stormier conditions to occur in the UK area. So it's a really interesting feature, and a lot of people are working on it. And it may also be connected to the fact that we have the last several years much warmer than normal temperatures off of the east coast of North America. So where I live here, the temperatures right now are running about 5 degrees warmer than normal, and they have been for several years. And that could be because the water that would normally go across the North Atlantic is being kind of blocked by this area of fresher, more buoyant water sitting on top of the North Atlantic. So it's a really interesting, evolving story.
Thank you.
All right, and Marilyn, I know you had a question in the chat too. Go ahead.
I've got several questions, and one was just a brief one. What's the time scale on that NASA simulation of the jet stream, sort of from the view from the pole? Is it over days, over months?
I think it's about 3 weeks. So between 2 and 3 weeks, I think, because it didn't actually give that information. And I've been asked that several times. But just knowing what I know about how those waves kind of evolve, I think it's probably in the order of 2 or 3 weeks.
Thank you. And my other question is probably a little longer, and perhaps you addressed it in the explanation to the Greenland cold spot, but you talked about the polar vortex splitting, the split pieces drift southward. Mm-hmm. And then later in that slide of the weak jet stream, you also had like 4 blobs of polar vortex. Why does it drift away from the pole?
Right. And so one of the reasons that it splits in the first place is because the stratosphere warms over the pole. And so the relatively cold air then is kind of pushed out of the way, if you will. So they've got to go somewhere, and they can't go north because they started in the North Pole, so they've got to go south. And so that's where they tend to end up and they generally end up over the continents. And part of that is because the continents are so much colder already than the ocean areas. And so, cold air tends to want to go where there's already cold air.
So it is both down and south. The cold air is going both towards gravity down and also south. Yeah,
so the polar vortex part itself does not go down so much. It more just migrates southward.
Okay.
But that tends to enhance the southward dip in the jet stream, which is lower in the atmosphere. And that also helps that cold air come down from the Arctic at lower levels.
Thank you.
Mm-hmm.
It looks like Hugh is next.
Yes, I had a question about population control. It always seems to me that dropping the population, or at least slowing it, would be a prime solution to all the problems you listed. And I'm always surprised with these talks why there's absolutely no mention of that. So I was curious what your opinion is on it and why you at least don't mention it in lectures and articles.
Mm-hmm. Right. So population control is not a straightforward problem. It certainly is at least partly related to the fact that we're seeing increased greenhouse gases in the atmosphere. But if you look at where most of that water in the bathtub, if you will, came from, it came from the developed countries where population is already slowed way down. So it's not only a question of population. The countries where population is exploding the fastest tend to be the places that have the lowest per capita emissions of greenhouse gases. So I agree that, I mean, there's all kinds of reasons to want to help these countries that are experiencing a large increase in population. And most of the time, you know, the women are not, they just don't have access to any birth control, and their religion may prevent it as well. But I think, you know, educating the women in some of these countries is really the only way to have any impact on the rapid population that, you know, most of them don't want to have 9 children. So if they had a way to control that, I'm pretty sure that they would welcome it, but it's just, it's not a simple question. It involves religion, it involves their culture, it involves their economics, their access to medication, you know, there's a lot to it. So yeah, it's not in my research realm, but there's a lot of other things that need to be done in addition that will have a bigger impact, in my view, on getting us back on that green curve.
Okay, and next question is from Shanna.
Greetings from Fairbanks, Alaska. Thank
Hi
you
there.
for this talk. My question is about cloud cover and haze and how that's changing, and do we have a good way to get accurate, widespread data about the changing amounts of sunlight actually reaching the Earth's surface?
Right, so there's a lot to that question, actually. We are seeing a decrease in the amount of particles in the atmosphere, especially since, say, the mid-70s or so, when it was sort of at a peak. And since then, our efforts to decrease pollution in the atmosphere have helped remove a lot of those particles in the atmosphere, which is actually helping to make global warming worse, because they used to reflect some of that sun's energy back to outer space, and now more of the sun's energy is actually getting through. The cloud story is also a very interesting one, because clouds do 2 things. They're white and they reflect sunlight, so they help cool the surface. But at night, they actually act more like greenhouse gases, and they act like a blanket and help trap heat by the surface. And you can think of your own experience where on a cloudy night, it tends to be warmer than on a very clear night. So those clouds actually help trap that warm air at nighttime. So as we see clouds responding to the change in climate, there's a big question about whether clouds are having a net warming effect or a net cooling effect. And because of this, you know, 2 really major offsetting properties that they have, it really has been difficult to answer that question. But from what I've read, the most recent studies suggest that actually the clouds are having an overall warming effect. So again, sort of piling on to the global warming story. And so they are also contributing to the warming. And especially in places like the Arctic, where it's dark for 6 months of the year, any changes in the cloud cover up there have a much bigger impact during the dark season. And we are seeing the clouds increasing up there, and definitely adding to the fact that the Arctic is warming so much faster.
Okay. There's a question in the chat. First, I wanted to draw your attention. Stefan has said that the timescale of the jet stream animation is June 10th to July 8th of 1988. So if you want to check, he put the link there in the chat.
Oh, I was close.
Yeah. And so there's
Good to know.
a question. A question from Kenny Blumenfeld that both Dr. Francis and participants, if you want to, if you see that in the chat and want to follow along, I'll read it to you. Kenny is either in an airport or on a plane right now, so glad he was able to join us live because I know he wasn't sure he could. So his question is there any research into the behavior of shortwave troughs that are embedded within or flow along or through the larger longwave troughs? Since shortwaves often deliver the actual and active weather, is there a reason to believe that the persistent patterns you have identified connote stormier or more active weather? We certainly have seen our share of persistent air mass regimes that were without much in the way of cyclone activity.
Right. So just to provide a little more explanation for people who aren't meteorologists in the crowd. So I talked a lot about those large waves in the jet stream. And what happens is there's little ripples that kind of flow through those waves. And those ripples, or short waves as he was describing them as, are the individual storms or individual high pressure areas that we would see on a weather map. And they actually kind of follow those bigger waves in the jet stream. So if you have the large scale wave basically parked in one place, and if we think of that schematic that I showed you with the big purple arrow, and that that part of the arrow over the East Coast was where I said it was the stormy part of the wave, that's where we would see these lows come rippling through the wave. And as they get to that part of it, they tend to intensify and go up the coast. And, you know, we might call them nor'easters if they strengthened enough. So I think the two are very much related. If we do have one of these persistent large waves in place, it can definitely mean that we're in a very stormy period for a long time. In fact, in 2018, anybody who was paying any attention will know that we got 6 nor'easters in New England that year. And it was because the wave really was parked almost identical to that purple one that I showed you in that schematic. And we just got nor'easter after nor'easter after nor'easter. So there is some interaction between the short waves and the large waves, but that is really getting into, you know, much more complicated dynamics for this conversation. But yeah, I do think there's a tendency for seeing these stormy periods lasting longer.
Great. All right. Thank you. I have a really weird question.
Go for it.
I'm not sure I should ask. I'm just thinking of my students and what we've been talking about in class. And we have a couple graduate programs, but one of them being a land and atmospheric science program. And so we get students with diverse backgrounds, and it's a whole lot of fun to talk about global issues. So I like your water vapor slides you showed at the beginning, because we've had a lot of discussion about that, because water vapor is so complicated and trends in it and what that means. Mm-hmm. It's you know, easy to see that the increasing water vapor will lead to increased global warming, but then what does that mean for weather, you know, and everything. And then we've recently been talking about geoengineering, and I think it's related to your cloud explanation. So we've been talking about the stratospheric sulfate injection to reduce the incoming shortwave radiation, which I've taught this course for 12 or 13 years, and it still seems like a wildly crazy a proposal to students, but I know that more and more people, policy-wise, are considering it as something more realistic. So I think that's interesting. But I guess I'm thinking, are there ways that humans might manage impacts of global warming that you might have, I'm just curious about your opinion. You know, I know people have discussed this and scientists have discussed it, but if that hill that you talked about with the Arctic warming, you know, weakens the jet stream, are there things we can do to strengthen it, to counteract it? Or do you think that really still the best thing we need to do is to just stop the warming in the Arctic?
The best thing to do is to stop the warming, period.
Okay.
That is, I mean, to think about further disrupting the climate system with some other artificial means, to me, seems ridiculous. And it would take resources that are already being squabbled over to the nth degree in Congress and taking them away to do what some people might think of as a quick fix. But it is not, because you would have to, first of all, you'd have to figure out how to keep it going for as far as the eye can see. And unless you couple it with a really dramatic reduction in the emissions of greenhouse gases, then the minute you stop putting those particles in the upper atmosphere, then you're going to get a huge rebound in the temperatures of the Earth, and at a much faster pace than even we've been seeing. It would be a very dramatic shift. Not only that, but it would more likely cause some disruptions to the weather patterns that we may not be able to identify as not being related to those particles being put up there. So if one country experienced just an unprecedented drought, their wheat crop failed, their people were experiencing famine, they might just go ahead and blame whatever countries got together to put those particles up there, because they could find somebody who would say, oh yeah, this is because they did that. It just opens up an incredible can of worms, in my view, and really all of our resources should be put directly towards curing the disease, if you will, the disease being that bathtub that's just got way too much water in it. I don't know if you guys realize it, but the amount of carbon dioxide that's in the atmosphere right now has not been seen for about 3 million years. It's been that long since there's been this much carbon dioxide in the atmosphere. And the temperatures of the Earth, and especially the oceans, just have not caught up to the fact that we have all this carbon dioxide in the atmosphere. So we're on this trajectory towards you know, a world that, you know, certainly humans haven't experienced, and almost, you know, all life has not experienced. So this is just to put it in even more context, looking back farther in time.
Thank you. Let's do there's one more question in the chat, and it's somewhat related. You just mentioned our focus on carbon dioxide as probably the most rapidly increasing greenhouse gas, but the question has to do with water vapor, which you pointed out was our strongest greenhouse gas. So maybe this question would help clarify that. He's asking, what is the relative contribution of water vapor as a greenhouse gas compared to fossil fuel-based gases that we've been focusing on in our efforts to prevent global warming? Mm-hmm. Could you give us just a quick little quantification maybe?
Yes, and I did actually dig up some numbers that I wrote in that Scientific American article, and I'm just trying to remember exactly what that was. So we've seen a 4% increase in the amount of carbon dioxide in water vapor in the atmosphere just in the last, like, say, the 1970s or so. And because a molecule of water vapor is just a much more effective absorber of those long waves of energy, it takes much less water vapor to cause the same amount of warming. And I can't remember the exact multiple, but it was a lot. So unfortunately, we can't extract water vapor from the atmosphere and you know, solve global warming. It's because it is responding to the warming due to the other greenhouse gases that we've put in there, mainly by burning fossil fuels. So the only way to reduce the amount of water vapor in the atmosphere really is to reduce the other greenhouse gases in the atmosphere. So, so go look at the article. I don't have it handy with me right now, but there is some actual numbers there about that.
Great, thanks. We will. We'll try to post a link to it too if we can't post the article itself. So thanks very much. Okay. Oh, Amy has put
Somebody
the
just
link
did.
in
Okay.
the chat. Thanks, Amy. All right. Well, please join me one more time in thanking Dr. Francis for this really fascinating discussion.